AP Chemistry, this is the week 26 quiz recap, and it's also a preview of the next quiz, which is on equilibrium. That's going to be on Tuesday, March the 11th. It's been pushed back from Monday by popular demand. And then there's going to be a complete comprehensive acid-base quiz on Friday, and that's going to be on March the 14th. All right, so let's get started with this. All right, so typical Rice table problem. You're giving initial concentrations of the reactants. So let's go ahead and just write this out. Initial concentrations, and you start with 0 there. Variables of change here. So it's minus x, coefficient is 1, minus x. And this is a product. That's why I like to draw the arrow to be sure you don't accidentally make that a minus. And it's got a coefficient of 2, so it's 2x. Okay, so go ahead and do the math here. All right. We're going to come down, way down here. And we're going to write the equilibrium equation, law of mass action equilibrium equation for this actual chemical equation. Now we're ready to go ahead and plug in the variables and the actual Kc, which is 50, stated up in the problem. All right, there you go. Now you don't need to use the simplifying assumption here, because you can turn this into a perfect square. So 2 squared is 4, x squared is x squared, so 4x squared on the top. And on the bottom, it's these two squared. Okay, now you come down, take the square root of both sides. Okay, so the square root of 4 is 2, and the square root of x squared is x. So up on the top, it becomes 2x. Down on the bottom, it's 2 minus x squared, so the square root of that is 2 minus x. And the square root of 50 is 7.07. Okay, now it's just an algebra problem. We'll come down here. Okay, so what I did is I multiplied both sides on the top by 2 minus x. So they're going to cancel on this side. And then I'm going to distribute this. So 2 times 7.07. Parentheses. So the 7.07, 2 times that is this. And then 0.707 minus x is that. Be sure to stay on screen here. So I'm going to add 7.07 x to both sides. Divide both sides by 9.07. Okay, and it cancels on this side, and x equals roughly, to two significant figures, 1.6. Okay? So, I'm going to come over here, and what we want to know is the concentration of HI. Don't worry about the 2. That has nothing to do with it. You just deal with this. It's 2 times 1.6, and that's going to equal 3.2 molar equals the concentration of HI. Okay, now the reason you could not use the simplification is 1.6 is not much smaller than 2. It's 80%. Okay, I'll just tell you that. It's 80% of 2. The 5% rule says it has to be less than 5%. It's nowhere near being less than 5%. And therefore, you can't use the simplification. You would have gotten an answer if you had eliminated these x's right here. That's way off, okay? So if I showed you the 5% rule, it would be 1.6. It's the value of x over the initial concentration of 2 times 100%, and that would equal 80%, okay? To use the simplification, you have to be less than 5%, not even close. All right, so that's that problem. We'll move on. Okay, let's read this problem. It says if the initial concentration of SO2 and O2 are 0.1, so I'm going to go ahead, let's write the reaction first. Okay, and we continue, and the equilibrium, that's a key, it's equilibrium concentration of SO3 is 0.075. So that goes down here because it's an equilibrium concentration. All right, then it wants you to calculate the value of Kc. So this is this is the other type of problem they could give you. You have to have actual numeric values for the equilibriums, and then you can plug them into the law of mass action to get the value of Kc. Most of the time the problem goes in the other direction. They give you the value of Kc and ask you to figure out some concentration, but here they're doing it this way, okay? So it's a little puzzle here. So you got to figure out how to fill in all these squares. So we start off, they didn't give us any initial concentration of SO3, so we're going to put 0. And if we start with 0 and we end up with 0.075, then this has to be plus 0.075. Okay, so I confused a lot of you by putting two x's and x's in here, that you found that confusing. So let's just forget about x's. Let's just deal with the relationships. If this is 2 and this is 1 and this is 2, then these two numbers, this one and this one, have to be the same because the relationship of the coefficients is the same. And since this coefficient, this 1 here, is half of this coefficient, then this number has to be half of this number, okay? All right, so I'm going to go ahead and I won't even deal with two x's and x's. So this is a 2 and this is a 2, so I'm going to come over here and this is going to be 0.075. However many moles, in other words, of this you got to have the same number of moles of this, okay? And so we have the same number. Now this should be a minus because it is being reduced. Now, however many moles of this you have, you're going to have half as many of O2 because this number is half this. So this number is going to be half of this number. And if you do that on your calculator, you get a minus 0.0375. That's half of 0.075. So now we just do a simple subtraction, and we just go ahead and do it. We don't write it as I was about to do. So let's go ahead and do the subtraction. So it's going to be 0.1 minus 0.0375 and 0.1 minus 0.075. Okay, and what we get here is 0.025, and what we get over here is 0.0625. So we have every number on our equilibrium line, so we can use those, plug them into the law of mass action for the concentrations, and come up with the Kc for this. Okay, so we're going to go ahead and write the law of mass action. That's going to equal, we're going to now plug in these values. Okay, and now we're ready to calculate the value of Kc. So do that on your calculator. This squared divided by this squared divided by, don't multiply, divided by this. Okay, sometimes I just say 0.075 times 0.075 divided by 0.025 divided by 0.025 divided by 0.0625. Okay, I want to avoid the square button. Sometimes it makes me a little nervous as to what's being squared. Okay? Okay, and we get the Kc is 144. No units of measure. Please do this calculation. Be sure you get that answer. If you don't, you're doing something wrong with this calculation. It's very easy to do that. Okay, problem number 3. I skipped over this one in class because it was very similar to number 1 and I wanted to get on some later problems, but let's go ahead and do it. Initial concentrations. So they're not the same this time. That's going to make this problem a little bit different. Coefficient 1, coefficient 1, coefficient 2. Okay, so be sure you understand this. Okay, how we got that. Now we write the law of mass action, and they give you a Kc value. But we're first going to write it in general equation terms. Okay, it looks like that. Now we're going to plug in the algebra and put the actual Kc value in. Okay, so here you don't have a perfect square situation on the bottom like you did in problem 1. So we're going to have to use a simplifying assumption. And again, if they ask, you're always going to be able to use it here. So we're going to go ahead and get rid of this x. We're going to assume it's very small compared to 0.1. Get rid of this one, assume it's very small compared to 0.14. You cannot get rid of an x when it's a multiplication situation, okay? So we're going to rewrite this down here, and this becomes 4x squared. And you can use regular parentheses at this point if you want. It's a math problem. Okay, so we're going to multiply both sides by 0.1 and 0.14 to make these cancel, and divide by 4 to make this cancel, so you end up with just x squared over here. Okay, so let's go ahead and do that. Cancel, 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 cancel. Now we have to do the same thing on this side, so... Okay, so 0.1 times 0.14 times 2.6 is what we're going to have here, and then we divide it by 4. Okay, so 0.1 times 0.14 times 2.6 divided by 4 is what you're going to put over on that side. Okay, and for all of this, we get 0.0091. And don't forget this. Don't forget the 10 to the minus 4. And that's going to equal x squared. So I'm going to bring it over. I'm going to flip the x squared over to the other side and take the square root. Okay, so go ahead and do that calculation to get... Okay, and what we get is square root of x squared is x, and the square root of this thing gives us, in scientific notation, 9.5 times 10 to the negative 4. Okay, and again, they're asking, as with problem 1, they want to know the concentration. Let's come down here. They want to know the concentration of HI. So you plug that x value in here, and that will give you the concentration of HI. So, okay, it's not 2HI, it's just the concentration of HI. But it's 2 times this. Multiply that, and you get 19. Okay, you come down, you got to adjust the decimal, make it a number between 1 and 9.9. So I'm going to move the decimal over in between the 1 and the 9. So I made this number smaller. 19 went down to 1.9. So I have to make this number 1 bigger. And that would be to the negative 3. And that equals the concentration. It should be molar. Put an M there. Concentration of HI. Okay, that's how you do that. Okay, so they're giving you initial concentrations, and they want to know the equilibrium concentration of NH3. Okay, so when you draw a Rice table, you don't have to draw the lines, but if you do draw the lines, draw them with a straight edge, okay, especially on the AP exam. Okay, I'm not going to draw the lines, I'm just going to do this. So here's the trick here. Let's write the equation. All right. Okay, so here's the concentration of N2. It's over on this side. Notice that. And I don't care about the significant figures, the trailing zeros. Just that's good enough here. All right, and then you start with 0 over here. So remember, this is a reversible reaction. It can run from product side over to reactant side. The thing that's going to allow that to happen, you treat it from the standpoint that if the only concentrations you have at the beginning are these two have to be decreasing, and this has to be increasing. There's no other choice that it has. Okay, so this is going to be, there's a 2 coefficient plus 2x. Okay, this is a coefficient of 1, it's going to be minus x. Coefficient of 3 is minus 3x, okay? So just, think about that for a second, okay? How this is working. It's just valid to turn this around. And I'm just going to make this point. I made it in class. You could turn this reaction around and call these the reactants. Okay, I could write this as 3H2. Now this is not a part of this problem. I'm just showing you something. N2. And that gives you 2NH3. You just reverse the reaction. Okay, and you'd have the same... Okay, well, I wrote this in reverse, but this is the 3H2 is 0.1, and the N2 is 0.5, and this is 0. So you can do it so it looks a little more like a normal reactants to products reaction. But if you do, you have to take the reciprocal of this. So that means the K equilibrium, the equilibrium constant, would equal 1 over 3.81. So it's legal to do that, but you have to change the equilibrium constant or it'll be totally wrong, okay? So anyway, that's just a side topic or just a side issue that deals with this. Okay, so let's keep going. Okay, there we go. So now we have our equilibrium algebraic expressions write the law of mass action. And again, it's products on top, reactants on bottom. Okay, there you go. So that's what it looks like. Now we plug in the expressions, and we use the actual equilibrium constant of 3.81. Down here is 2x, and you have to square this, and I did not put the cubed here, so it's cubed right there. Okay, all right, so that's what that looks like. All right, so now we're going to use simplifying assumption. Otherwise we end up with probably something worse than a quadratic because there's a cubic there. So we're going to get rid of this and get rid of this, rewrite it down below. I'm going to go to parentheses, doesn't matter. Okay, and cube this, come down here, and this is 4x squared. 2 squared is 4, and x squared is x squared. Okay, so it's an algebra problem at this point. So what we want is we want to solve for x squared. So what we're going to do first is multiply both sides by x squared to get it up on the top over there. This will cancel. Okay, now we want x squared and everything else over on the right side, so we're going to divide both sides by 3.81. Okay, and what you end up with is x squared equals everything over here. So let's first multiply all of this and figure out what it equals. Okay, so I think I did something with the computer turned off. It's just math though. Okay, so we multiplied both sides by x squared here and canceled on the right side. End up x squared equals times 3.81. Then we divided both sides by 3.81. And when you do all that, you end up with x squared by itself over here and everything else over on this side. So the first thing we did is just do the math on this first before you do the square root. And you end up with 3.3 times 10 to the negative 5. Now you take the square root of that down here. We're doing that. And so we're going to do that right now. And we end up with 5.7 times 10 to the negative third for x. Okay. We go back up. What we're looking for is the concentration of NH3. So it's 2 NH3. So NH3 would come down, or rather if we come down here, NH3, the equilibrium concentration is 2x. So now we come down here and 2x equals, and that's going to equal 11.4 times 10 to the negative 3. Okay, and you need to slide that decimal over to make it a number between 1 and 9.9. So it's 1.14 times 10. You made this number smaller, went from 11.4 to 1.14, so you got to make this number bigger, and that's to the negative 2. That's molar, and that's your final answer. And I'm off screen. Doggone it. Okay, there we go. And that's the concentration of NH3. Not of 2NH3, just of NH3. Okay, there's your final answer. Okay, good. Okay, now solubility products. We're going to do 2 of these because they're 2 different things they could ask you, and only 2. There's no other third thing. They're either going to ask you for the KSP and give you the molar solubility, or they're going to give you the molar solubility and ask for the KSP. Okay, so that's what they're doing here. They're giving you the KSP right there, solubility product. So again, what this is you look at your solubility rules. This is a compound that's insoluble. It should not dissolve. However, in the real world, it dissolves a little tiny bit. So these are very small, generally pretty small equilibrium constants. And when it dissolves, it's going to produce this. So we know that chlorine has to have a -1 charge, and you have 2 of them. So that means you have 2 -1 charges. That tells you that the lead you're dealing with, lead can have more than 1 possible charge, has to be a 2+. So again, this is 2 times 1 minus becomes 2 minus. Therefore, this has to be a 2+ charge here. And they're both aqueous, but this is a solid. We call it a solid. It's supposed to be a solid, but in the real world, it does dissolve a little bit. So let's go ahead and plug in the numbers. Okay, and they give you the KSP for PbCl2, lead 2 chloride. And what's the molar solubility? Now, what is the molar solubility? It's this number here. This is usually a number on the change line we don't care much about. We're interested in the initial, we were given the initial, and we're interested in getting to the equilibrium. This is just kind of an intermediate step. But this is actually a significant number in these types of problems. So we're going to call it, we're going to first put the, it says 0.2 molar. And then the coefficient is 1, so it's going to be minus, but we're going to use S. Because you could use X, perfectly fine, except this tells you that it's a molar solubility. It's something special. It's not just another random variable that's a change variable, okay? So down here you got this. Okay, and we start off when we put the lead chloride in the solution or in the water, there you have nothing of this at the beginning, okay? And so this is going to be a plus S, and this is a plus S, and so down at the bottom you have S and you have S. All right, and we're interested in finding out what S is. So let's go ahead and write the law of mass action for this, for the solubility product. Okay, these are the easiest problems once you do a few of them and get the hang. Okay, so you have the products over here. They're both aqueous. Don't let the ion numbers scare you. They have nothing to do with it. And it's Cl1 minus. But what's important is that coefficient is a 2, so you put a square there. Okay, again, the coefficient goes up there. Now, the reactant is a solid, so you do not include it in this. So it's only these two, and that's always true in a solubility product, okay? All right, so now we're ready to plug in some numbers here. So we've got the KSP. Okay, and so again, this becomes very simple. It's S times S is S squared. I'm going to move that over to this side. S squared equals this. Okay, so we got to take the square root of both sides. And that will give us S. And this one's a big enough number, I'll just go ahead and write it in decimal. It's 0.015 is S, and that's what you're looking for. It's S here and here, and so that's the S, but really this is what you wanted to know, but it's also S. It's how much of this solid dissolved. That's what it's telling you. And that much, and it should be in molar. So molar, that's how much dissolved. So that's what you were looking for, the molar solubility. This is the molar solubility. All right. Okay, we got another solubility product, except they're going in the other direction. This time they're giving you the molar solubility, that number right there, and they're asking you to find the KSP. All right, so write the reaction. Okay, so it's MnCO3, and one of the things you should have memorized is carbonate is a 2-. That means manganese is a 2+. Now, anyway, so that's 2-, 2+. So that's part of knowing your charge numbers. And this is a solid, and it's going to produce this. Okay, there you go. There's the reaction, the law of mass action. Again, you don't include a solid. Okay, and it gives you the KSP, or excuse me, it does not. You're trying to find that. So, okay, and there it is. So we're going to go ahead and write the reaction out here. And we start with 0.3 molar of this, and we have the molar solubility. It's this. That's the number that goes in there. This number up here. Over here we start off with this, and we add the molar solubility because the coefficients are all 1s. Okay, so we have everything on the equilibrium line. We have to do a little math on this one, except this is a solid, so it's not going to be a part of the equation, so we can ignore it. So how do we find the so again, we're just going to work with these two. All right, so here we go. Again, it's just this multiplied by this. In other words, those two are the same number, so you square it. And that's all you do, and once you do that, you have the answer. Okay, and what we get for KSP to two significant figures is 1.8 times 10 to the negative 11th. Very small number, okay? And that is the final answer for that. So these are pretty easy once you know how to do them. Okay, now we're going to move on to some Le Chatelier principles. So here's just a generic kind of a reaction. It's an exothermic reaction. Heat comes out of it. Okay, so the first three deal with concentrations. With concentration, I'll write it up here. It's the crowded room metaphor. Okay, the reaction wants to move away from the more crowded. If you increase the concentration, it wants to move away from that, the crowded room. And if you decrease the concentration on one side, that room becomes less crowded, so it wants to move toward a less crowded room. Okay, so in this case, concentration of A is increased, so that makes the reactant side more crowded, more concentrated, so it's going to move towards, remember these terms, favor products. It means move towards the products. And again, let me clarify what that means. It doesn't necessarily mean it's going to start making more products. If it was in a situation where it was actually going backwards here and making more reactants, and then you increase the concentration of this, it may continue to make more reactants, but it'll do it more slowly. It's slowing down. So that's why you don't say it's moving to the left or moving to the right. You say favors products, okay? So making this side more crowded favors products. Concentration of C is increased, so that's on the product side. You made this room over here more crowded, so that's going to favor reactants. Okay, concentration of D is decreased. It's on the product side, so that makes this room over here less crowded, so the people want to move to the less crowded room, so that's going to favor products. Okay, so this is an exothermic reaction. Now we're going to deal with temperature, which means you treat heat as a product. Heat wants to come out of this reaction. That's what a negative delta H means, and it's what exothermic means. Heat wants to come out. So heat wants to come out of this. So what happens if you increase the temperature of the overall reaction? It makes it harder for heat to come out. You're shoving heat. What you're doing with a higher temperature out here is you're shoving heat back into the reaction, and it's making it harder for it to come out. So if you increase the temperature of an exothermic reaction, that's going to favor reactants. It's going to tend to want to move to the left or favor to the reactant side. If you decrease the temperature, now heat wants to come out, and it wants to come out into a really cold room. So it's very easy for the heat to come out if this surroundings out here is cold, so that is going to favor products. And you notice I wrote originally plus heat. That you don't normally write that when you write a chemical reaction, but I did it to emphasize that an exothermic reaction wants to have heat come out as a product, as part of the reaction moving from left to right. Okay, let's go ahead and do a few more. Okay, so here's an actual reaction. Now this is a gas. These are gases. It's also exothermic. So concentration, so the same thing can apply even though it's gases for concentrations. So the concentration of N2O2, this is increased. So this side becomes more crowded. So everybody wants to move over to the left. So that's going to favor reactants. Okay, concentration of N2O2 is decreased. So you made this room less crowded. So everybody's going to want to move toward the less crowded room. So that favors products. Concentration of NO2 is increased, this one. That makes this side more crowded. Everybody's going to want to move over to the products. Okay, concentration of NO2 decreased. You made this room less crowded, so everybody wants to move over to the less crowded room, so that's going to favor reactants. Okay, here we go again. Temperature is increased. So this is exothermic, so I could write plus heat. Heat is one of the products of this reaction. So you get out N2O2 plus heat in an exothermic reaction. So if the temperature is increased, you're trying to shove heat back into it, okay? You're making it really hot outside, so heat is trying to be forced back in. So that's going to push the reaction backwards, so that's going to favor reactants. So again, that's turning on a heater in a very hot room. It's going to be hard for the heat to come out into a room that's already hot. Okay, temperature's decreased, so now it's a really cold room. It likes to give off heat. It's much easier for a heater to give off heat in a really cold room, so that's going to favor products. Okay? And pressure is increased. So this is the new one. This applies only to gases. So here's PV equals nRT. You got to remember this little story. Okay, so the pressure is increased. So you increased the pressure. Okay, so well, how did you do that? Maybe you reduced the volume and squeezed it down, okay? So you increased pressure, okay? The reaction says, I don't want my pressure increased. I want to go back to my old pressure. So reaction wants to decrease pressure back to where it was before. Okay, well, what does it have control over? The reaction doesn't have control over the temperature. R is a constant. It doesn't have control over volume. You do. You can change the volume. The one thing it can control that can affect the pressure is the number of moles. So if the number of moles, so if we write this again, this is what the reaction is going to do. It's going to say, I want to reduce my pressure, so I'm going to reduce N. And mathematically, if you say cut this number in half, you've got to cut something on this side in half, and in case the volume's fixed, it's going to be the pressure. So the one thing the reaction controls is the number of moles. It can move back and forth between a side with more moles and a side with fewer moles. Okay, so if it decreases the number of moles, it will do what it wants to do, which is decrease the pressure. Okay, so in this case, this side has 2 moles, this side has 1 mole. You increase the pressure, it wants to decrease it, so it wants to go more to the direction of fewer moles. 1 mole versus 2 moles, so this is going to favor products. Again, think about that. Be sure it makes sense. Okay, pressure is decreased. All right, so PV equals nRT. You decrease the pressure. The reaction says, I don't want my pressure decreased. I want to go back up to my old pressure. So it wants to go to the side with more moles. So it'll move from this side toward this side. So that's going to favor reactants. Okay, so be sure you understand all these Le Chatelier for concentration, temperature, and pressure. Be sure you understand. They're pretty easy. You just have to practice them and think about them a little. Okay, that takes care of this review. This is what your test on Tuesday is going to basically include. All right.